Hi everyone, let's take a closer look at the atom. And before we do this, perhaps you should go back and look at that video where we discussed atoms and review what we mean by protons, neutrons, and electrons. So here's the link. Okay, so in a little bit more detail, it turns out that the number of protons in an atom is really what determines the type of atom that you have. And each type of atom is called an element. And all the known elements are listed on the periodic table of elements. So here's a simple periodic table, and all the atoms that only have one proton are called hydrogen. All the atoms that have just 8 protons, those are called oxygen. Ooh, and here's a fun one. If you can find some atoms with 79 protons, those are gold. And the chemical symbol for gold is written in the old, I think it's Latin, abbreviation. Now for exams, you'll get this periodic table. Here in each cell, you get a lot of information at a glance. At the top is the atomic number, so 92 here for uranium. The symbol is U. The name, that's helpful. The name is uranium, written right there. And then something called atomic weight is also listed on this periodic table. Now it's an interesting question to ask, how were atoms made? In order to get 79 protons inside of a gold atom, all those protons have the same charge, and like charges repel. So how did these protons all get pushed together against the repulsive force? Well, the theory is that the heavier elements must have been made by huge gravitational forces inside stars. And then those stars exploded in a supernova and were spread across the universe. Here's some terms that you need to know. Atomic number is the number of protons in an atom. And because electrons are 1/2000th the weight of a proton, and protons equal neutrons in weight, then to get the weight of an atom, just add up the protons and neutrons. And that number is called the mass number. Sure, get the mass of an atom. Just add up the protons and neutrons that make up its nucleus. Each of these elements can weigh different amounts if they have different numbers of neutrons. And those atoms with different weights are called isotopes. They have the same number of protons, same type, same element, but they weigh different amounts because they have different numbers of neutrons. And then finally, if one element with lots of different atoms of different weights, then it might be interesting to get the average mass. And that's called atomic mass or atomic weight. And again, it's an average of all the isotopes of an element. Okay, if we want to collect all this data about atoms and write it all down, here's one way to record it. It's called using the chemical symbol. And so go to the periodic table, look up a particular type of atom, and write down its symbol. And then if you also want to note down how many protons are there, you can write the atomic number in the lower left as a subscript. The mass number for your element of choice can be listed up on top as a superscript on the left. That's the mass number. And then when the number of electrons does not equal the number of protons, the atom will have a charge. There'll be a net charge. And you can list that in the top right. And then finally we'll learn later, well actually at the end of this recording, that atoms stick to other atoms to form molecules. And so sometimes you need to record how many atoms are present. And that's a number listed on the bottom right. Number of atoms that make up a particular molecule. Okay, that's a lot of information. Why don't we break it down a little bit more easily. And we're looking here at lithium. We can go to the periodic table and look up what Li stands for. It stands for lithium. And let me ask you this. How many neutrons are in this isotope of lithium? Did you say 4? Take 7 minus 3 equals 4. The mass number, how heavy the atom is, depends on the number of protons. And since neutrons weigh as much as a proton, 3 plus 4 equals 7. That's how heavy this isotope is. Okay, let's do another example, kind of using these terms all together. It turns out that there are 3 isotopes of hydrogen. And they have names. You do not have to memorize these names. But there's protium, deuterium, and tritium. Well, how are they alike? Well, they're all hydrogen. So the atomic number is 1. Yeah, hydrogen are those atoms that have 1 proton. Okay, and so protium, deuterium, tritium are just specific names for the isotopes of hydrogen. They are hydrogen because they have one proton. How are they different? Well, that's in the number of neutrons. Turns out protium doesn't have any neutrons. You look in the nucleus, you only see one proton. There's a heavier form of hydrogen, however, that does have a neutron. You look in its nucleus, there's a proton with a neutron. That's called deuterium. And then there's a third form where there's two neutrons in there. That's tritium. And it turns out that two neutrons and one proton don't get along so well in the nucleus. Yeah, it turns out that tritium is radioactive. We'll talk about radioactivity in another chapter. Okay, this is enough information to construct part of the chemical symbol. Okay, what's the symbol from the periodic table? Well, look at the atomic number. It's 1. So go to the first element on the periodic table. That's hydrogen. So the symbol for all three of these is H. They are hydrogen. Let's write down the atomic number. That goes in the bottom left. So what's the atomic number for protium? 1. Atomic number of deuterium? 1. The atomic number for tritium? 1. And that was kind of boring. And you might start to see that the atomic number and the chemical symbol kind of say the same thing. So oftentimes we just leave off the atomic number, so that if you know that the element is H, you can go to the periodic table and look up the atomic number. Okay, let's find the mass number, the top left number. Well, the mass number is how heavy the atom is, and that's simply just add up the protons and the neutrons. 1 plus 0 is 1. Deuterium has a neutron in it. It's twice as heavy. Tritium is 3 times heavy, right? 2 neutrons, 1 proton, mass is 3. There you go. Those are the 3 isotopes of hydrogen. And they just get a little bit fatter with those neutrons. They're just carrying neutrons carry no charge. Just add weight. Okay, using a mass spectrometer, and you can go back and look at the chapter 9 magnetism to see how a mass spectrometer works. We can measure the masses of atoms. And so it turns out that if you put a bunch of hydrogen atoms in a spectrometer, there are a lot of hydrogens out there that don't have any neutrons. Protium is the most common form of hydrogen. In fact, about 99% of the hydrogen atoms out there are protium. They don't have neutrons. And roughly about 1% is deuterium. And on rare times, you can find a trace amount of tritium, which is actually pretty good, right? Because tritium is radioactive. You don't want a bunch of that found in your water, because water is H2O, right? Lots of hydrogen in water. Okay, finally, let's talk a little bit about the atomic mass or atomic weight. And remember, that's the average. We see that if you have protium, the weight is going to be 1, mass number 1. But if you have deuterium, the mass number is 2. And then let's just ignore the tritium, because that's so rare, we don't expect to see any of it. Let's say we go grab 100 hydrogen atoms just at random. So if it's totally random, we expect to get about 99 out of those 100 hydrogen atoms to have no neutrons. And then maybe 1% of 100 would have a single neutron in it. That would be a deuterium atom. Let's calculate the average. To get an average, you add up all the weights, total mass, and you divide by a total number. So let's do that. For the first 99 atoms, they all weigh mass number 1. So there's 99 atoms that weigh 1. 99 times 1. The last atom, atom number 100, is deuterium. Well, the mass number is 2. The total number of atoms, well, that's 100 atoms. And 99 times 1 is 99, plus 2 is 101. And we divide that by 100. And you can get your calculator out, or just realize that 100 just slides the decimal place over 2. The atomic mass is the average weight of a hydrogen atom, and on average, it's 1.01. So 1.01, how does that compare to the periodic table? Well, you can see the number here for hydrogen in the upper left of the table is 1.0079, and hey, that rounds off to 1.01. Exploring the atoms in more detail, let's talk about those electrons. Where are they? Well, there's something called the shell model. It's based on experimental data, And it tries to get at how the electrons are arranged inside the atom. And it turns out that the electrons appear to be arranged in shells or layers, and the electrons that are in the highest shell, at the surface of the atom, those are called the valence electrons. The outermost electrons are the valence electrons. And how do they get there? How do they get so far away from the center of the atom where all the protons, the positive charges are that are attracting those electrons? Well, those outermost electrons must have a lot of energy, a lot of kinetic energy, and they sped up and flew farther away. And the slower moving electrons, ones with less energy, they must be closer. So electrons in higher shells have greater energy. And it turns out once electrons have been placed in a shell, it can move out of that shell. If it can somehow gain some more energy, it can go farther away from the nucleus and jump into a higher shell. How does it gain more energy? By absorbing light. So move to higher shells by absorbing light. And if an electron wants to drop down to a lower shell, it needs to slow down. It needs to lose energy so it can emit or give off light and move to a lower shell. And we know from an earlier chapter that light has energy, and it's dependent on the frequency of light, how fast it vibrates. Faster vibrations, more energy. And then our eyes can actually perceive that energy and tell different colors. So different frequencies have different colors. One more fact is that the electrons in these shells have specific amounts of energy. So if you're looking at one type of atom, a certain number of protons, the atomic number gives the specific type of an atom, that the electrons are going to be attracted to that certain number of protons, more attraction, and that helps determine the energy of each shell. And it turns out that electrons in a particular shell have a specific amount, one amount of energy, and each shell has its own specific amount. And there are only certain numbers of shells there. You can't have all possible combinations. That's what the data tells us. So each transition between a shell requires a specific amount of energy. And each atom is going to absorb or emit particular energies of light, or in other words, different colors. Okay, let's review that a little bit more. Here's a picture of the shell model, quite simple one where we're just looking at the interior and the outermost electrons. And you got hydrogen here with one electron, one proton. Helium has two. And it turns out the first shell is filled at 2 electrons. So then you start filling a second shell in the second row. And then nature then says, okay, for some reason the second shell is full. So let's start filling the third shell. So you go down the third row. And an interesting pattern comes out of this. As you look at each column, they end up with the same number of outermost electrons. They have the same number of valence electrons. Hydrogen, lithium, sodium all have 1 electron on the surface. If you go to fluorine, F, and chlorine, Cl, they both have 7 electrons on the surface. Same number of valence electrons. Okay, how do electrons move between the shells? Well, light energy comes in, and the electrons can absorb that light energy if the energy of light matches the amount of energy it needs to jump to the next shell. If that light has too much or too little energy, the electron won't absorb it. It'll be transparent. The light will just pass through. But if the energy of light matches, then the electron can absorb it and jump to the next shell. And then later it can say, hey, I want to go back down. So it can release light, emit energy, slow down, and drop back down to that lower shell. And so every time an electron in this picture drops from the second to the first shell, the exact amount of energy is released. And the energy is frequency, it's proportional to frequency, which means a particular color comes out. Now if an electron moves between different levels of shells, well, a bigger drop is going to mean a bigger change of energy. And so the frequency it comes out of an electron dropping from shell 7 down to shell 2 is going to be huge. It's a lot of energy. So a huge amount of energy of light means very high frequency. It's vibrating very quickly. And then if you drop between adjacent shells, not so much energy. That's going to be a lower frequency, right? The red wavelengths are really low wavelengths, long wavelengths, slow frequencies. The blues, Lots of energy. So when you cause hydrogen to glow, it turns out it glows with particular energies. Heat up these electrons, they jump between the shells. The shells have specific amounts of energy, so you only get out specific colors. And in the visible spectrum, the colors that we can see with our eye, we can only see five colors for hydrogen atoms. If you switch to other elements, well, they have different numbers of protons, so their shell energies are different, and they give off different colors of light as electrons bounce among those shells. So here's calcium, different colors, lithium, strontium, sodium, and then on your own, why don't you take a look at this last one? It's a combination of two of the elements above. And by matching the colors, you should be able to figure out which two elements produce this spectrum down here. We've said that atoms are too small to see. How come? Well, if you look at the wavelengths of visible light, they're too big. They're so much bigger than the size of an atom. And so the visible light doesn't reflect off the atom because it's too small. The wavelengths just kind of go over the atom. So we can't directly see light. However, we could indirectly see them with a fancy device called a scanning probe microscope. And this is one way you can set it up. You can put your material that you want to look at, the collection of atoms, and then you get this really tiny little lever, and you create a tiny tip at the base right here such that there's a single atom at the tip. And then you move the sample underneath the tip and use a device called a piezoelectric device. Piezo means a kind of squeeze. It's a neat material that when you squeeze on it, it gives off electricity. But you can also apply electricity and that'll squeeze it. And by applying electric current very carefully, you can squeeze and move the base here, which slides the sample around. And as you move the sample around, this tip right here is kind of dragged along the surface. Remember, the surface of the atoms contain valence electrons, and electrons repel electrons. And so as you move this tip, the electrons of each atom, the tip and the surface, will repel, and that will move this little lever. It bends a little bit, and you can use a laser to reflect off of here and watch that tip move. And you can measure how much it moves as you drag the tip near the surface, and you get the repulsion. And you can make a little map of the surface. So here's some maps. You can see tiny little individual atoms in here, a little mountain of atoms piled up. Here's another material. The atoms are shaped in, or arranged into hexagons. There's a defect, a missing atom there. And for other materials where the atoms are loosely bound on the surface, you can use that atomic force microscope to slide the atoms around. So here scientists had some fun arranging atoms into a ring. Right, we're getting some waves on the surface of the material as the vibrational waves are bouncing against this wall of atoms. So like on little waves on a pond. Okay, last idea. Atoms stick to other atoms to form molecules. They're chemically bonded together. And so the tiniest piece of water consists of two hydrogens attached to an oxygen atom. That's H2O, right? There's a chemical formula. And in this formula it says, hey, you have hydrogen, there's two of them. The number to the bottom right lists how many atoms you have, two H's, and there's also one O. If you want to look at blood sugar, also known as glucose, here it is, it's C6H12O6. There's 6 carbon atoms, 12 hydrogens, and 6 oxygens. Okay, that's all for now.